Okay, thanks, Peter. So I think roughly this time last year, where I was at the conference for James Oxley in Louisiana, and I put out, I think, what I call a call to arms for people to work on the excluded minors, GF5 representability. And Rutger and Jeff both stepped forward to work on it. Since then, Dylan has joined us, and I believe Matt Croker will also join us. So the problem is just to find the set of excluded minors for the class of GF5 representable matroids. The excluded minors have been found for fields of size 2, 3, and 4. And when I first met Tut, I think it was about 1997 or so, so Dan Younger introduced me to Tut, and when he introduced me, he said to Tut that I had just solved the excluded minor problem with Bert and AJ for the excluded minor for GF4 representability, and Tut said, the next case, which left me completely deflated. And so who knows why on earth I want to do yet the next case, but I really do. And it's really a good time to work on the next case because there's this nice arithmetic progression here, 1958, 79, 2000, and clearly like next year's the year, right? I mean, that's clearly now is the right time to be working on the excluded minor problem. Unfortunately, these are publication dates, so it's probably, or we've probably already missed the boat. Anyway, maybe we can get fast publication when the editor sees this beautiful arithmetic progression. I'll just push the paper through. So how many excluded minors do we expect? Well, again, we go to the arithmetic progression that you see before you, and clearly there's going to be about 10, actually probably exactly 10. Unfortunately, that's not quite the case. We know a little bit about the excluded minors thanks to a computer search. So Dylan Mayhew and Gordon Royal did a search of all matroids up to 9 elements. There's an enormous number of them, and they found the excluded minors. And even on 9 elements, there's 456. There's even a few more known. So Nick Britell did a search. He was looking through a subclass of GF5 representable matroids for various partial fields. He found an additional 294 excluded minors of size 10, but that's just a partial list, so we don't know how many there are of size 10. I would really like to know what this is going to start looking like. Is it going to start closing off soon? Or is it just going to keep blowing out for a while and then close off? So I have a URA working on this, and I thought we would be able to find the excluded minors on size 11 and 12, etc. But it turns out that I'm not very good at computing. So all we've managed to do so far, and this is with Rutger and my student, Timothy Wayuda. So we've actually got all of the rank 3 ones at least. And there they are listed by size. The one of size 11, by the way, is a matroid that we've seen in recent weeks. It's a reed geometry. So it's not representable over any fields because there's no fields of characteristic 4. So it's the reed geometry for 4. So I would like to push this out and see where things are going. So again, as I say, hopefully we're going to be able to do a computer search for matroids up to, say, size 14. It seems pretty clear that if we are going to find the excluded minors for GF5 representability, computers are going to need to play a substantial role because there's an enormous number of these things. But it does also put forward the question, how useful would an excluded minor characterization be? Right? There's an enormous number of excluded minors, so you can actually use the excluded minor characterization for GF4. You can break it into the case that you've got some problem you want to solve, and you can think about which matroids are GF4 representable, and the representation can help you solve the problem. And if you're not representable, you contain one of 7 excluded minors, and then you can use those minors to to help you with the problem. But when you've got this number of excluded minors, you have to wonder, what's the utility? But I do hope that maybe by going back and looking at the excluded minor characterization, we might be able to derive more useful characterizations. So for example, if you take so here's a non-representable matroid, it's the non-pappus. For this to be representable, you would need those 3 points through the middle to be on a line. But if you take the proof that this isn't representable, the proof doesn't care whether or not these 3 points are right. The 3 points on that red line are collinear or not. So whether or not you have that collinearity, the matroid's still not representable. And there's 2 other lines there that you can put in if you wish. So there's actually 4 matroids there, whether you've got 0, 1, 2, 3, or 4 of those red lines, sorry, 0, 1, 2, or 3 of those red lines in, that are all not representable, but for the same reason. So maybe by going back and searching through the excluded minors and comparing excluded minors with other excluded minors, we might be able to get a more sort of coherent explanation for why matroids aren't representable over GF5. And I kind of imagine computers being used in that part of the problem as well. And there are other things you might try. So for example, here's a result that you can get from the excluded minors for GF4 representability. There are 7 excluded minors for GF4 representability. And if you take duality into account, there are still 5 of them. But if you're looking at large 3-connected matroids, you can reduce that number to 3 excluded minors. So you only have to exclude the 6-point line, P6, and the non-Fano. So maybe we can prove something like that for GF5 representability after we've got the list of excluded minors. We can go back and see which ones are required for large 3-connected, or let's say large 4-connected matroids maybe. And then maybe the list will get down to something more manageable that you'll actually be able to use for various things. And there's even other things you can do. So for example, this set of excluded minors is closed under delta Y operations. And here U26 and P6 are delta Y equivalent. And so in a sense, you can even reduce it down to a list of size 2 if you're dealing with a problem for which delta Y equivalence is natural. Okay, so that's a little bit just about where I hope this will go. So now, in terms of this talk, what I want to do is to give you a sketch of the proof of the excluded minor characterization for GF4, and then look at which of those ideas extend to GF5 representability, and then focus. So something that comes up in the proof is the notion of a bad determinant, and then we'll focus on what the structure might be for bad determinants. And at this stage, we don't know a whole lot, but at least I think that it gives a good strategy for dealing with the excluded minor problem. All right, so I want to work towards proving the excluded minor characterization for GF4. And let's suppose we've done a case analysis and we already know what happens for matroids of up to 8 elements. So let's take an excluded minor with at least 9 elements. It's easy to prove that excluded minors are 3-connected. And of course, you have to have a U24 minor, because if you don't have a U24 minor, you're already binary. And if you're binary, you're GF4 representable too. So our excluded minor is 3-connected and has a U24 minor. The nice thing about that is that U24 is the stabilizer for the class of GF4 representable matroids. And what that means is that if you tell me the representation of a U24 minor within your matroid, within a 3-connected matroid, the representation of the U24 minor essentially determines the rest of the representation uniquely. So to be precise about that, take a 3-connected GF4 representable matroid, and now I can always find a basis so that to get the U24 minor, so n is the U24 minor, to get the U24 minor, I'm only contracting elements from the basis and only deleting elements from outside the basis. So that when you look at a representation with this property, so I do row operations so that I get an identity corresponding to the basis, and I'm going to suppress that identity throughout this talk. So this is to get a representation here, you'd be putting in an identity in front and labeling those columns with B. So now I can see my stabilizer relative to this basis B. And if you take a representation, all I need to know is the representation on the stabilizer, and that will uniquely determine the rest up to column scale. That's what it means to be a stabilizer. And if you look at U24 over GF4, it actually has two representations that are inequivalent up to scaling, but they're related by field automorphism. And so that tells you that every three connected GF4 representable matroid has a unique representation up to the choice of basis, scaling, and field automorphism. And that's really, really useful. So in improving excluded minor type results, unique representability is sort of fundamental. Same way as if you're trying to prove Kuratowski's theorem, it's typically fundamental to know that three connected planar graphs have unique embeddings. But it's sort of that kind of thing. Okay, so how do you use this? Well, it turns out that you can find two elements. Well, after duality, you can find a pair of elements whose deletion leave you three connected and leave you with a U24 minor. Okay. Now, this is an excluded minor. So if I delete either E or F, I have a GF4 representable matroid. And if I delete both E and F, I get a GF4 representable matroid. But that matroid, because N is a stabilizer, has a unique representation. So I can assume, so that when I look at when I delete E and when I delete F, I get the same. I can assume that I'm getting the same representation on M delete EF. I just apply a field automorphism and scaling to one of the matrices. And then I can put those two things together and I can get a GF4 representable matroid that agrees with M when I delete either E or F. Right, so basically I find this thing that's sort of wanting to be a representation of M. This is the representation of M when you delete either E or F. Okay, but it's not a representation of M, and that means that somewhere something went wrong. So there's going to be some, well, basis that's a basis in, there's to be some set to basis in exactly one of these two matroids. And in terms of that representation, that matrix representation we're looking at, that says there's a square submatrix where either it's singular when it should be non-singular or vice versa. And I call that a bad subdeterminant. There's a subdeterminant where for my excluded minor, it wants that subdeterminant to be either singular where it's non-singular or non-singular where it should be singular. And that bad subdeterminant necessarily contains both E and F, because when I delete E or F, I have a representation. Okay. And now what you want to do, you've got this fixed basis, and now you want to change that basis to make this subdeterminant small. Ideally 2 by 2 would be great. Can't be smaller than that because your bad determinant has to contain E and F. So we try and change the basis. Unfortunately, when you do that, you don't see the stabilizer anymore. Right? So we started out with the stabilizer being visible. We chose the basis in a careful way so that we could see the stabilizer. And then we had this bad determinant come up and we pivoted so that the bad determinant was small, but then we lost sight of the stabilizer. And so that brings about the problem, which I call the intertwining problem, and that's the problem of making the bad determinant small while keeping the stabilizer visible. Okay. And this is really the crux of the problem. Not for GF4, but when you're trying to apply this for GF5. Over GF4, it turns out that it's sort of not that difficult, and that's because the stabilizer is U24, and U24 is an excluded minor for binary, and binary is a subfield of GF4. So seeing when a matrix is binary, so if I would give you a matroid over GF4 and I want to know whether it's binary if and only if it can be scaled to be binary. And so you end up with a fairly simple structure that it basically has to be a cycle in the associated fundamental graph that can't be scaled away. So this problem turns out to be easy for GF4, but difficult for GF5. What you have, when you put all these things together, you've actually got a sort of a certificate of non-representability for your excluded minor. So I get a unique, so this matrix gets filled in uniquely. So having the stabilizer and these two elements, E and F, whose deletion leave you 3 connected, basically enables you to fill in a unique candidate representation. Right, so this portion of the matrix is unique because of 3 connectivity and the fact that N's got a unique representation. And then those representations extend uniquely to E and F. So that would be a unique candidate representation for M. But the bad determinant is a proof that your matroid isn't this candidate representation. And so that's a proof that your matroid is not representable. And so the idea of the proof is to find such certificate in a minor. So you try to build this certificate. And of course, when you build it, that has to be your whole matroid. But you've built this up structurally. And so now you know the structure of your matroid, your excluded minor. Right, so so you start out and just look at you've solved the intertwining problem. You've got the bad determinant small at the same time as seeing your stabilizer. And now you say, well, I've got my bad determinant, my stabilizer in this minor. I just focus on the union of the bad determinant and the stabilizer, and I ask, well, does that satisfy the connectivity condition that I needed? And so namely, if I take that, exclude that little minor, and I remove E and F, am I still 3 connected? If the answer is yes, then when I look at that little minor, it's already not representable. So, well, okay, maybe it isn't 3 connected, so I have to add a few things in to repair the connectivity. But then after I add in the stuff that repairs the connectivity, now I know that that gray thing is not representable because it contains the stabilizer, the bad determinant, and it satisfies the connectivity properties. And so it had to be the whole lot. And this repairing connectivities was the difficult part over GF4. So basically all the work went into solving that problem. However, it was really mechanical. So even though there was the difficult part over GF4, it was the kind of thing that one could easily put into a computer. And so in general, it's not the crux of the problem. The crux of the problem is really this intertwining issue. All right, so that was GF4. And now let's see what happens when you work over GF5. So over GF5, you first of all want to break your problem up into different parts. So we consider excluded minors that don't have a U24 minor. And then you consider excluded minors that have a U24 but don't contain the 5-point line or its dual as a minor. And then you consider excluded minors that have a 5-point line minor. So in the first case, you're essentially finding the excluded minors for regular matroids because a GF5 representable matroid is regular if and only if it has no U24 minor. So this first case is the same as finding excluded minors for regular matroids. And the second case, the GF5 representable matroid is dyadic if and only if it doesn't have a 5-point line or its dual as a minor. The dyadic ones are the GF5 representable matroids that are representable over GF3. They're also the matroids that are representable over all fields except those of characteristic, except possibly those of characteristic 2. So the excluded minors for regular matroids we already know, that's a result of Tuts. And the excluded minors for dyadic matroids we don't know. I remember when I first met Jeff Whittle back in 1990-something, our very first discussion was about finding the excluded minors for dyadic matroids. I just found the excluded minors for GF4 representable matroids, and a lot of the ideas carried over to dyadic matroids. And we basically felt like that this problem would fall over quickly. It's now quite a lot later and it hasn't fallen over yet, but I do think that its days are numbered. So hopefully we can at least do that. And then of course there's the general case, and hopefully we'll also do that. So what's nice for GF5 is that the whole theory of stabilizers carries over beautifully to GF5. It turns out that it all falls in a heap for GF7 and larger fields. So over GF7, it's already the case that 3 connectivity is not enough to bound the number of inequivalent representations, but even if you sort of take a higher notion of connectivity, the whole notion of stabilizers fails. But at least for GF5, we still have a theory of stabilizers. So the 5-point line is a stabilizer for the class of GF5 representable matroids. And if you don't have the 5-point line or its dual is a minor, then U24 is a stabilizer. So that's nice. Like for all the cases we care about, we have a nice theory of stabilizers there. Now you can look at the 5-point line, and it's got 6 inequivalent representations over GF5, and the 4-point line has 3 inequivalent representations. So that says that 3 connected matroids have at most 6 inequivalent representations over GF5. So that's nice, but it's slightly problematic if we think about the proof technique we were applying for GF4, because 6 isn't 1. Right? For GF4, we relied heavily on having a unique representation. And here we don't have a unique representation. So what do you do there? What you can do is you can take your stabilizer, so say it's U25, so it's got 6 inequivalent representations. Just take one of those representations and ask, why doesn't that representation extend? And if you do that, then everything works. So I can find a certificate why that representation doesn't extend. And then the idea is to find a small certificate that doesn't extend. And then after I find a small certificate that representation doesn't extend, I now have a matroid that's a stabilizer again, because if you contain a stabilizer, you are a stabilizer. If I have a stabilizer sitting in a bigger 3-connected matroid, the bigger 3-connected matroid is also a stabilizer. So I still have a stabilizer, but it has fewer inequivalent representations. And so you can repeat the proof where the answer to the first part question becomes the input to the second part. So now I take a different representation of this matroid and I repeat. And every time I repeat this, I get fewer inequivalent representations. So what you see is that the proof is basically going to be a whole bunch of repeated proofs of the same type that we did for GF4. So there was only one case for GF4. There's going to be a load of cases for GF5, and unfortunately, sort of the outputs to every time you kill a representation, all of the minimal things for that are going to go into the next phase as a new case. So there could potentially be a load of cases that we have to solve. Okay. So the problem that we're going to have to solve again and again and again is this intertwining problem. I've got my stabilizer, which is a moving target, and this bad determinant, and I want to ask how small can I make the bad determinant while keeping the stabilizer visible? The traditional approach for this has been to basically look at the stabilizer and ask what stops me from being able to see it. So like if I build up, what are the fragile matroids for that stabilizer? So I've got a bigger minor, and however I remove anybody, I can only remove elements in one way to keep the stabilizer. And the problem with that approach is that we're going to have lots of different stabilizers, and you don't want to ask that question every time. Every time you ask that question, you're going to have to go away and do a whole bunch of work that's particular to the stabilizer. So what we're proposing is to do the same kind of thing, except focus on the bad determinant. And the thing with the bad determinant is it's just it's not going to change from question to question. It's just like a submatrix where it's singular where it should be non-singular. So that the structure of that matrix isn't going to change terribly from one application to the next. So I'm looking at minimal bad determinants. So I can just basically, I can focus on this bad determinant here. I can delete the other elements that aren't in the basis and contract the other elements that are in the basis. And so then I can do the same thing in the excluded minor. When I remove elements from the excluded minor, I'm going to get a GF5 representable matroid. So I end up with two matrices where I have a GF5. In one case, I get a singular matrix. In the other case, I have a non-singular matrix. And for all of the other submatrices, they're going to have for all of the corresponding pairs of submatrices, they're going to have the same rank, except for when I look at the whole matrix. All right, so I've got two matrices over GF5. One's singular, one's non-singular. But if I were to look at some submatrix of the left one, and then take the corresponding submatrix of the right one, they would have the same rank, unless it's the whole lot. So that's what a bad determinant corresponds to. So I can take the corresponding matroids. So now I've got two matroids on the same ground set. And because these are square matrices, the rank's half the number of elements. The set C is a circuit hyperplane. Well, they differ in a single thing, and the only way for two matroids of the same rank to differ on a single set is that you have a circuit hyperplane in one matroid and a basis in the other. So M2 is obtained from M1 by relaxing a circuit hyperplane. So that's what we have when we're looking at bad determinants. So if I'm trying to solve the bad determinant question over GF5, I need to understand pairs of GF5 representable matroids with this property. Two matroids are related by a circuit hyperplane relaxation, and you're in the case that the rank is half the number of elements. Okay. So in general, we know that circuit hyperplane relaxation doesn't behave nicely with respect to representability. So for example, going from the pappus to the non-pappus. When you take a circuit hyperplane, this circuit hyperplane in the pappus, you relax it, you get a non-representable matrix. But what's sort of more surprising is that over small fields, if you relax a circuit hyperplane, the matroid you get really doesn't want to be representable in some sense. So if I'm working over a small field and I relax a circuit hyperplane and I get another matroid that's still representable, the two matroids have to be massively structured. So here are a couple of examples of that. The first is a result of Trumper, who explains what's going on over GF3. So here's a general result, but let me just say it in the three connected case. If you have two GF3 representable matroids and one is obtained, two 3 connected GF3 representable matroids and one is obtained from the other by a circuit hyperplane relaxation, then one of them is a wheel and the other one's a whirl. massively structured. And there's a more recent result of Clark, Oxley, and Van Zwam that explains what's going on for GF4. And they show that over GF4, if you've got these two matroids related by two GF4 representable matroids that are related by relaxing a circuit hyperplane, then both of the matroids have path width 3. It's enough for the more relaxed one to have path width 3 because it implies the other one. What does it mean to have path width 3? It means you've got an ordering of the elements where no matter where you split the ordering into an initial segment and a final segment, you'll have a 3 separation. So as I move the elements across one by one, I keep a 3 separation in my matrix. So they had a precise characterization, and they derived this as a consequence. But it turns out that this is already essentially a characterization. So the opposite of a circuit hyperplane, so in the relaxed matroid, you've got what's called a free basis. So a free basis is a basis that you can relax into a circuit, or you can tighten into a circuit. So if you have a GF4 representable matroid with a free basis, the tightening of that to a circuit hyperplane is going to be GF4 representable if and only if your matroid had path width 3. So this is really basically a characterization. The proof of this was fairly long and relied on a computer search. We have well, we don't have a simpler proof of this theorem exactly. We throw in an extra assumption, but we do have something that I'll show you in a little while. So the problem we want to solve is this. I want to characterize the pairs of GF5 representable matroids where one is obtained from the other by relaxing a circuit hyperplane. And if it helps, you can assume that the rank's half the number of elements, because that's what you get in the bad determinant case. Right, so that's really the thing we need to solve. So let me explain our approach to this problem for the GF4 problem, and then come back to GF5 in a while. So I'm not going to quite prove the result for GF4. I'm going to throw in the condition that the rank's half the number of elements. And why that's useful is because it's easy to deduce from that that M2 is 3 connected. Without the condition that the rank's half the number of elements, just the fact that you've got a circuit hyperplane whose relaxed, just the fact that you have a circuit hyperplane means that you're 3 connected up to series pairs. And if your rank's half the number of elements, basically means that you have the same thing in the dual. So you're 3 connected. Okay. So let's look at this as a bad determinant now. So I've got these 2 representations. With this minimal bad determinant over GF4. The first thing I do is change the basis so that the bad determinant becomes 1 by 1. So it's a 1 by 1 bad determinant. It's a matrix which is 0. So one of the matrices you have a 0, and the other one you have a non-zero. Of course, I can scale the non-zero to be 1. You can't have any other zeros in that row or column, because if you had another 0, you would be forced to have a whole row of zeros, because the 2 by 2 matrices have to either both be singular or non-singular in both. So if you think about that, you can't have a, if you had a 0 in that position, you can't have a non-zero over there. Otherwise, that together with this would give you a non-singular matrix here and a singular matrix here. so that you get, so in that row and column, you don't have any more non-zeros, and you can scale them all to be ones. Excuse me. Right. Here's where we use the rank being half the number of elements. It turns out in that case that you can find elements, you can find these elements E and F, so there was a bit of freedom about how you went down to the 1-by-1 case. If the rank's half the number of elements, you can choose E and F so that when you delete E and contract F, you're close to being 3 connected, and by close I mean up to series and parallel elements. And you have a U2-4 minor. But U2, the 4.9 is a stabilizer, and that means that the matrices A1 and A2 are going to be equivalent up to scaling and field automorphisms. So you can actually apply these and get them the same. So I can apply scaling and field automorphisms in one of the matrices, and I can reduce to the case that these two matrices are identical except in that bottom left corner. So I've got two identical matrices, and I just change one entry from a 0 to a 1, or we're saying going from the right to the left, the 1 to a 0. And when I change this one entry, I've got the surprising property that I'm not changing the rank of any submatrix, except for that 1-by-1 submatrix. Right, that's what's going on here. So it's a fairly particular property to have for a matrix, a fairly difficult property to have for a matrix. And it turns out that over GF4, the only way for this to happen is that this matrix A tilde has the property that every submatrix has a constant row or column. And how do you prove that? Well, you first need to prove that if you give me a big matrix or any matrix which has got no constant row or column, then it has a 2-by-2 or 3-by-3 submatrix with no constant row or column. Right, so this is just repeat that. If you give me any matrix with no constant row or constant column, it contains a 2-by-2 or a 3-by-3 submatrix with no constant row or constant column. If you're looking for something fun to entertain yourself with, it's a nice thing to prove. It's a very short proof, and it's nice. And these are the only ways you can actually have matrices, so 2-by-2 and 3-by-3 matrices with no constant row or column. Okay, so now if I want to prove that previous result, I just need to consider all submatrices that look like this. So for example, let's just do one case. Let's look at this case here, and let's look at a submatrix of the form. Let's take B equal to 0 and A equal to omega. I plug that. I take that matrix, and I look at the determinant. And in the left case, the determinant is 0. In the right case, the determinant is omega plus 1. That's not allowed, right? The only two submatrices where they're allowed to have different, have one singular and one non-singular was the 1-by-1 submatrices. So that's a problem. That doesn't work. Now, if you try all of the other cases, and there's quite a few other cases, you get that there is no submatrix with no constant. Every submatrix has to have a constant row or column. Now, when I say there's a lot of cases, there's some symmetries here I'm not telling you about. So actually, you don't have to consider, like if you think about the number of cases, you'd have to consider it was quite a few. So one thing that's already easy to see in this matrix back here is that the matrix A tilde can't contain any ones. So all the entries are 0, 1, or omega. And then there's a sort of a scaling you can apply on the matrix, but I don't want to go into the details of that. It's not exactly a scaling. Anyway, there aren't that many cases to consider, and you prove that you end up proving that every submatrix of A tilde as a constant row or column. And now you think about what such a matrix has to look like. So maybe it's got a constant row, you pull that out. Whatever's left has to have a constant row or column. Say it's got a constant column, delete that. What's left has got a constant column, delete that, etc. This gives you a linear ordering of the elements because you keep on looking at the matrix, finding a constant row or column and deleting it. So that gives you a linear ordering. And that linear ordering, you can easily see, gives you path width 3 in the Matroid M2. To get the result for GF3, it's basically the same, but things work out even nicer because you only had the 3 possible values for GF3, and you weren't allowed to use 1 in that in the top right submatrix. So you only have 1s and 0s, and then that matrix is actually forced to be triangular. And then from that, you easily see that you get the Matroids you're looking at are a wheel and a whirl. So the GF3 and GF4 cases come easily out of this analysis. You can do basically the same thing over GF5. So you start out with your bad determinant. You can pivot it down so that your bad determinant becomes 1 by 1, and then the same things that I was saying earlier are true. You can scale to get the 0, 1 pattern there. And then things get slightly more complicated. So you can choose E and F so that when you remove E and F, they leave you essentially 3 connected and leave you with a stabilizer for whichever case you're dealing with. You don't have field automorphisms to work with, so instead of thinking about fields, you need to think about partial fields, which I'm not going to go into. And it turns out in the dyadic case, so the dyadic case turns out to be the case where M1 doesn't have a U25 or U25 minor, then you can get A1 equal to A2 up to, you can just get that by applying a partial field automorphism. In the general case, I don't know how to get those 2 matrices the same, and there's a problem with when you get too many nested partial fields. But you end up with quite a bit. I mean, I know that at least A1 and A2 tilde are, A1 tilde and A2 tilde will be related by some partial field automorphism, which is slightly weaker, which would require a bit more case analysis. But it still should be quite should be enough to, we should be able to figure out what's going on. But at the moment, we'd be already very happy if we could do dyadic. So we're focusing on matrices that have this form. So I've got these 2 different matrices. I've got these 2 matrices over GF5. And basically I have a 1 in a position and I replace it with a 0. And the only submatrix whose rank changes is that 1 by 1 submatrix. Right, so what we want to know now is what's the structure of these things. Unfortunately, you can apply that previous result about things with constant rows and columns, and it's not enough. There are some of those matrices work. There will be examples you can plug in where you don't get any contradictions. And so basically, at the moment we're in the point of we're still trying to figure out what the answer should look like, and we're using computing for that. We know a few. Actually, I don't think we haven't proved any. There are infinite classes of 4 connected matroids that come up, but at least we believe there are infinite classes of 4 connected matroids that come up. We haven't proved anything about them yet. But they should be highly structured. And I don't think it'll go beyond, I don't think there'll be like anything higher than 4 connected. I think there'll be infinite classes of 5 connected things coming up. So we're basically in the process of doing computing to tell us what the answer is going to look like, and then we hope to prove what the answer looks like. Yeah, and that's where I'll stop. Thanks.
Thank you, Jim. Are there any questions? I'll ask a provocative one. Do you think humans will ever know them for GF7?
Ever's a long time. Mind you, ever for humans may not be that long. So that's I mean, there's different questions about how long you think people will be around for, but I mean, assuming that we're around for a long time, probably, I would guess probably no, but I don't. I still think no, but it seems a bit arrogant to say no, because hopefully we learn things. I mean, if we're going to be around for a while, hopefully we're not just developing better and better texting thumbs or anything like that, right? I mean, hopefully we develop in other ways and can do better mathematics.
Are there any real questions?
Yeah, what do you expect the size of the biggest excluded minor to be?
Well, that's what I don't really know. There's this, at the moment, we seem to be, when you look at the numbers, we seem to be looking at the bottom of an ice cream cone. And I'm kind of hoping the big fat top's coming up pretty soon. I'll go out on a limb, I'll say 15.
Okay. What do your co-authors think?
Well, they wouldn't, I mean, my co-authors are careful people. They wouldn't go around saying stupid things like that.
Okay.
There's no way it's going to be an odd number, right? I mean, you would, yeah, I think that you'd be more likely right than wrong there. But you never know, right? I mean, it could just be one thing that's sitting there for some crazy reason, like the reed geometry is sort of poking out a long way. Like in rank 3, we get this 11 element thing that's way further than you would expect in rank 3. And it's because the reasoning behind the reed geometry is sort of complex. There's this one Matroid that forces characteristic fall through a complex sequence of things. So I don't know why there wouldn't be one Matroid floating around. It's certainly true that I certainly expect that there will be a lot of Matroids of a certain size. And so the last place where you get a lot of Matroids, the rank will be equal to the co-rank. But I don't know why you wouldn't get one strange one poking out, or like a few strange ones poking out past that.
There's another question from Nathan. He says, you said you don't think there'll be infinite classes of highly connected examples of bad determinants for GF5, but do you think there'll be a bound on the path width?
If you believe that I can prove things without making too many mistakes in the past, so roughly I claim to have already proved that with Bert Gerards and Jeff Whittle as part of Matroid Minors, that there's a bound on path width. But you know, I'm not going to ask anybody to take any leaps of faith there. But I claim that I can prove that.
Are there any more questions?
I have something that's, I think, probably an ill-formed or stupid question, but it seems to me you sort of have two ways that things can fail to be representable. One of them is just a size constraint. So like a uniform Matroid, just, there's not enough stuff in the field to work. And then the other one is this sort of bad determinant where you've got, a circuit hyperplane versus a basis. It looks like it's the second kind that sort of predominates in these excluded minors. Is that just sort of intuitively clear, or is that right?
The bad determinant isn't, so the bad determinant comes up even in the size cases. So the bad determinant is just part of your excluded minor. So it's part of the explanation as to why your excluded minor is not representable. And that comes up in all excluded minors, whatever the reason. But I think there are, there are, as far as if you look at excluded minors, there seem to be two kinds of excluded minors, actually three kinds. So there's the excluded minors that are there purely for size reasons. Then there's ones that are there because of algebraic reasons, that they satisfy a certain equation. That, like in fields where you can satisfy a certain equation, you have them, and when you can't satisfy them, when you don't, in fields where you don't satisfy that equation, you don't have them. So you get excluded minors for that reason. And then you get the Pappas Matroid. That's the third class, the Pappas Matroid. So the Pappas Matroid is an excluded minor for G of 5, but it's representable over G of 4, and it's representable over all fields of size bigger than 5. So that seems to be the three classes.
Thanks.
Stefan says, is attacking Hydra 5 or 2 regular still considered an intermediate step?
I wasn't talking much about partial fields, but when you follow the approach that I'm saying, you are finding the excluded minors for partial fields, because the Matroids with a U25 minor with 4 inequivalent representations belong to a certain partial field. And therefore, when you're killing off one representation, you're pushing yourself out of that partial field. And so you can, from that, deduce the excluded minors for the partial field. So everything that I've said, you could restate in terms of partial fields. But I don't think one needs to think about the partial fields. So I think that if you didn't know about partial fields, you could reasonably find the excluded minors for G of 5. Knowing about partial fields, you might find them in a slightly more sophisticated way. So there'll be things that there'll be double work you do if you don't know about partial fields. And there'll be partial field results that, so going back, in this case here, for the dyadic case, for getting A1 equal to A2, that's using a partial field automorphism. Now, you didn't need to use the partial field automorphism. You could have just gone away and done the work, but you'd be doing double work. Like you'd be doing a lot more work to look at the cases where these matrices are different when there's no reason to. They might as well just be the same. So you'll be doing a lot more work in that case to actually figure out what the bad determinants are when you could have saved yourself some time. So partial fields are a more refined way of going through things that save you a bit of work.
Are there any more questions?
Yep. I've just, first of all, a comment. Jim, I remember that conversation we had about the dyadic partial fields as if it were yesterday, but I think it was a few more days ago.
Like you said it, now we're going to do it.
Yeah, well, that's right. Time's running out in more, but anyhow, for some, anyhow. Yeah, but the issue of about how large excluded minors might get, I mean, the partial field hierarchy does give you an idea. Have you thought about, I think we talked about, have you thought about looking at just using it to find an example of a relatively large excluded minor? So you do something like start off with this Hydra 5 layer and find an excluded, just find one and keep using that as a stabilizer and seeing if you can just go through your...
I tried to do that. That was something else. I mean, I was planning on doing all sorts of, that was one of the things I was planning to do this summer, but I had to, I was unreasonably optimistic about the amount of computation I was going to be able to get done this summer. Turns out that computing is not so straightforward, and it takes time.
Yeah.
Yeah, so there was a bunch of things I was hoping that we would get done, and like heuristically looking for excluded minors was definitely one of the things that I was hoping to do to see if things did get large. I do kind of feel like you'd be a bit unlucky if things really did fit together. So I mean, you could imagine that you have excluded minors fitting together in some sort of sequence, and you sort of say, well, let's suppose that they work in the best possible way so that every time you're increasing by, say, 2 elements, and then you go through 5 layers or 6 layers to get to the excluded minor, then you're going to get quite a big excluded minor by the time you get to the end of it. It'll be, what, 5 plus 12, 17 elements.
But there are some scary excluded minors for dyadic, aren't there? It just, isn't it? There's some calculation about that.
Yeah, there's a 16 element one.
Ah, right, yeah.
Well, that seems to shoot down my 15 element bound.
That's right.
So Rutger was probably sitting there remembering the 16 element one. I even knew the 16 element one. I just forgot it when I answered. Yeah, I don't know how big they're going to get. They're not going to get too big though. I mean, I really believe they'll nearly all die out by about 13, 14 size. That's my guess.
Are you talking about the coronavirus?
No, that'll clearly be, we'll have a vaccine by the end of the year for sure.
You're wasted in Matroid theory, mate.
Are there any more questions before I end the recording?
Your president assures me that it's not an issue.